What's going on, guys? In this video we're going to be covering hierarchical clustering, which is another method we can use to group our observations based off similarity. So in order to understand hierarchical clustering, we first have to understand what a dendrogram is. So dendrogram is the output we're going to receive after we run our hierarchical cluster model. So the way it works is all observations start out in their own groups. So here we have observation 1, observation 2, observation 3, and so on, so on, so on. Now, as we work our way up the dendrogram, these observations are going to be fused together. So at this point, observations 2 and 3 would be fused together. At this point, we'd have observations 1, 2, and 3 fused together. At this point, 1, 2, 3, and 5 would be fused together. And we keep doing this until all observations ultimately get grouped together. Now, looking at this dendrogram, we can see that observation 7 and observation 9 are the most similar of any observations. Now this is because they're going to fuse first, where they have the lowest point on the y-axis where they fuse. Now as we work our way up this dendrogram, we can see next they're going to fuse with observation 4, and then with observation 6. So by the time it gets to observation 6, we can no longer say that it's the most similar to observation 4, even though it's nearest in height, because it's already grouped with observations 4, 7, and 9. So by the time it gets to fuse with observation 6, we can say it's no more similar, or we can say that observation 6 is no more similar to observation 4 than it is to observation 7 and observation 9. So after we create our dendrogram, we can choose how many groups we want in our data. And the way we do this is by creating a horizontal split in our dendrogram. So say we just cut at this point here. So this means all observations below the lines will get grouped together. So for instance, at this point, all observations that are already grouped together will form one group. So we could say that group 1 would have observations 1, 2, 3, and 5, because they already fused together below this line. So group 1, we're on observation 1, 2, 3, and 5. For group 2, it would be all observations that already fused below this branch. So we'd have observations 6, 4, 7, and 9. And then finally, for group 3, it would be all the observations that fuse below this branch. So we'd have 8, 10, and 11. So just like in k-means clustering, the number of groups can be somewhat arbitrary. But unlike k-means clustering, we can choose the number of groups we want after we already created or ran our model. Now choosing the number of groups can be somewhat arbitrary, but in this instance I would think that 3 would be the correct number of groups because we're ultimately going to end up with these 3 different subgroups of data. So now how do we group our observations? So in order to group our observations, we need both a similarity measure and we need a linkage function. So similarity measure, the most common, and the way that we're going to solve our problems is with Euclidean distance. And another method you could use is going to be the correlation. And then for linkage function, we're going to have 4 options. We're going to have single, complete, average, and centroid. So when we're using Euclidean distance, it ultimately finds the distance between 2 points of data, or 2 points in space. But here we're going to have 2 groupings of data. So we can't just find the distance between one observation and a different observation because we have choices. We can either find the distance between this observation and this observation, and this observation and this observation, or the distance between this observation and this observation, and the distance between this observation and this observation. So ultimately we have 4 choices, so which one do we use for our Euclidean distance? So that's where our linkage functions come in. So what our linkage functions say is, between our 4 possible choices, if we're using single linkage, then we're going to take the minimum value. If we're taking complete linkage, we're going to take the maximum value. If we're taking average, we're just going to take the average value. And if we're using centroids, it's a little different. We're going to find the difference between the centroids of the two groups. So we're going to have 4 distance measures. So let's call this observation 1, observation 2, observation 3, and observation 4. So the 4 possible Euclidean distances we can find is from observation 1 to observation 3, observation 1 to observation 4, observation 2 to observation 3, and observation 2 to observation 4. So now we just have to find the Euclidean distance for these measures. So from observation 1 to observation 4, so we're going to go from to observation 3. So we're going to go from 0, 2, or x1 value of 0, x2 value of 2, to an x1 value of 2, x2 value of 4. So for Euclidean distance, this is just going to be 0 minus 2 squared plus 2 minus 4 squared. And then we're going to take the square root of this. And this will produce a value of the square root of 8. And then if we go from observation 1 to observation 4, it's going to be 0 minus 4 squared plus 2 minus 6 squared. And then take the square root, and we'll get the square root of 32. And then if we go from observation 2 to observation 3, so from 1, 3 to 2, 4, it's going to be 1 minus 2 squared plus 3 minus 4 squared. Take the square root, and this will give a value of the square root of 2. And then finally, from observation 2 to observation 4, it's going to be 1 minus 4 squared plus 3 minus 6 squared. I'll take the square root, and this will give a value of the square root of 18. So now that we found our Euclidean distances, we can apply our linkage functions. So you're only going to choose one linkage function, one similarity measure. But here I'm going to show what the different results will be for each of the different linkage functions. So the first one we'll do is complete. So for complete, we're going to choose the minimum of these values, or the closest distance between the two groups, which we can see is the square root of 2. So for the minimum of these values, we would get the square root of 2, which is observation 2 to observation 3. So the height that these two would fuse on our dendrogram would be at a height of square root of 2, which is equal to about 1.41. So if we were to draw that, these two groups would fuse at a height of 1.41. So now if instead we use complete, then we're going to take the highest value. So the highest value we can see is the square root of 32, which is just equal to 5.66. So if we were to draw that dendrogram, then they would fuse at a height of 5.66. And then for average, we're going to take the average of all these 4 values. So it would just be the square root of 8 plus the square root of 32 plus the square root of 2 plus the square root of 18 over 4. And this is going to produce a value of 3.53. So these observations would fuse at a height of 3.53 if we use the average method. And then finally, centroids, which is a little bit different than the other ones. So in order to find centroid differences, first we have to calculate the centroids of each of the groups. So we're going to have observations 0, 2, and 1, 3 in our first group, And our second group, we have observations 2, 4, 4, 6. So we find the centroids, it's just going to be our middle values. So for 0 and 1, the average is going to be 0.5 for x1. For x2, the average value is just 2.5. And then for our second centroid, it would just be 3, 5. So now that we found our centroids, we have to find the Euclidean distance between our centroids. So unlike with the other three methods, where we're either going to find the minimum value of these four possible, or the maximum value of these four possible, or just average them all together, with centroids, we're finding these two new numbers, our centroids, and then we're going to take the Euclidean distance of these centroids. So for the Euclidean distance, it's going to be 0.5 minus 3 squared plus 2.5 minus 5 squared. We'll take the square root, and this will give a value of 3.54. So they'd fuse at a height of 3.54. So notice that the average and the centroid fused about the same heights. The complete is the highest, and then the single was the lowest height, which makes sense because this is going to take the minimum value, the highest value, and then the average value and the centroid value ultimately usually end up being pretty close. So now we're going to create a dendrogram from scratch, and we're going to use Euclidean distance as our similarity measure again, and we're going to use our single linkage function, which is going to be the minimum value. So each of the observations is going to start out in its own group. So for group 1, we're just going to have observation 1, or 0, 0. For group 2, we're going to have the second observation, or 1, 2. For group 3, we'll have observation 2, 6. And finally, for group 4, we'll have observation 3, 9. So now in order to find the first fuse, or grouping we'll make, we define the smallest difference, or smallest similarity measure, which we're using as Euclidean distance. So whichever one of these groupings has the smallest Euclidean distance from each other, we'll group first. So our options. We can go from group 1 to group 2. We can go from group 1 to group 3. We can go from group 1 to group 4. Or we can go from group 2 to group 3, group 2 to group 4, or finally from group 3 to group 4. So we're going to have 6 different choices. So we just have to find these Euclidean distances and then choose the smallest of them. So from group 1 to group 2, it would just be 0 minus 1 squared plus 0 minus 2 squared, and then we'll take the square root. And this will produce a value of the square root of 5. From group 1 to group 3, it would just be 0 minus 2 squared plus 0 minus 6 squared. Take the square root, and we'll get a value of the square root of 40. From group 1 to group 4 was 0 minus 3 squared plus 0 minus 9 squared, square root, and we'll get a value of square root of 90. And now from group 2 to group 3, 1 minus 2 squared plus 2 minus 6 squared, square root, get square root of 17. From group 2 to group 4, 1 minus 3 squared plus 2 minus 9 squared, square root, we'll get the square root of 53. And then finally from group 3 to group 4, so 2 minus 3 squared plus 6 minus 9 squared, and take the square root, and we'll get square root of 10. So now, in order to choose the most similar two observations, we're going to take the minimum of these values. So the smallest value is going to be the square root of 5, which is just equal to 2.24. So if we were to draw that on our dendrogram, at a height of 2.24, group 1 and group 2 merge, so this is just going to be observations 1 and 2. So that's going to be our first grouping. So now in order to find the next grouping, we're now going to have only 3 groups. So in group 1, we're going to have observations 1 and 2, which was 0, 0, and 1, 2. In group 2, we're going to have observation 2, 6, and in group 3, we're going to have observation 3, 9. So now again, we have to find the Euclidean distance between each of these 3 different groups and choose the smallest value. So our choices, we can go from group 1 to group 2, we can go from group 1 to group 3, or we can go from group 2 to group 3. So now we only have 3 possible choices. So the first step, we'll find the Euclidean distances from group 1 to group 2. But notice now, group 1 has a group with more than one observation. So we have to find the Euclidean distance from 0, 0 to 2, 6, and from 1, 2 to 2, 6. And since the linkage function we're using is single, we're going to take the minimum of these 2 values. So first we'll find the Euclidean distance between these 2. So from 0 to 2 squared plus 0 minus 6 squared, square root. So that's one possible value. And the other one is going to be 1 minus 2 squared plus 2 minus 6 squared. Take the square root, so that's our other possible value. So now, since we're using single linkage, we're going to take the minimum of these values. So this amounts to the square root of 40 and the square root of 17. So since the square root of 17 is less, that's going to be our distance we're going to use between group 1 and group 2. So now to do the same thing for group 1 and group 3. So again, group 1 is 2 observations, so we have to find the minimum of the 2 distances. So the minimum of 0 minus 3 squared plus 0 minus 9 squared, square root, and 1 minus 3 squared, and 2 minus 9 squared, square root. So we take the minimum of these 2 possible values, which is going to be the square root of 90 and the square root of 53. We would take the square root of 53 because we're using single. Now if we were using complete instead of single, for these 2 we would be taking the square root of 90 and the square root of 40, since those are the bigger of the 2. Since we're using single, we're taking the smaller. And then finally from group 2 to group 3. So each only has 1 observation, so it's just going to be basic Euclidean distance. So 2 minus 3 squared plus 6 minus 9 squared. And we take the square root, and this will give a value of the square root of 10. So now we compare 3 choices, or 3 groupings. We can either take the square root of 17, square root of 53, or square root of 10. So since the square root of 10 is the smallest value, that's the next grouping we're going to do. And the square root of 10 is equal to about 3.16. So now if we draw that on our dendrogram, so at 3.16, so group 2 and group 3 are going to merge. So that is going to be observation 2 and 3. I mean 3 and 4 from group 2 and 3. Okay, so there's our second grouping. So now we only have 2 groups left. So we can only form one more grouping. So we have group 1 and group 2. So in group 1, we have observations 0, 0, and we have observations 1, 2. In group 2, we have observations 2, 6, and observations 3, 9. So now in order to form our Euclidean distances between these 2 groups, so from group 1 to group 2, we're going to have 4 possible choices. We can go from observation 1 to observation 3, observation 1 to observation 4, or from observation 2 to observation 3, observation 2 to observation 4. And since we're using single linkage, we're going to choose whichever one of these produces the smallest Euclidean distance. So start with observation 1 to observation 3. So it's going to be 0 minus 2 squared plus 0 minus 6 squared. And I'll take the square root of it. So that's our first choice. Now our second choice, we'll do observation 1 to observation 4. So 0 minus 3 squared plus 0 minus 9 squared. We'll take the square root of it. Now our third choice, so we'll do from observation 2 to observation 3. So 1 minus 2 squared plus 2 minus 6 squared, square root of it. And then finally from observation 2 to observation 4. So 1 minus 3 squared plus 2 minus 9 squared. I'll take the square root. So now if we plug in and solve for these, we will get the square root of 40, the square root of 90, square root of 17, and the square root of 53. So since we're using single, we're going to choose the smallest of these values, which is just going to be the square root of 17, which is equal to about 4.12. So now we can complete our dendrogram. So at a height of 4.12, these two groupings will merge. And then there's our final dendrogram. So then after we create our dendrogram, now we can create our horizontal split and form how many groups we want our observations to be into. So on the exam, you might be given a picture of a dendrogram and asked which linkage function was most likely used to create it. So here we're going to have 4 different dendrograms, each with a different linkage function, and all created from the same data. So we'll start with the single. So notice when we use a single linkage function that all our data tends to tail off to the right. So with single, often you end up with an unbalanced dendrogram. The next one we look at is centroid. Now with centroid, anytime you have these weird little like upward boxing looking things, which are called inversions, you know it's centroid, because centroid is the only one that can cause these inversions. And in the next example, we'll show how these happen, or what causes these. Now the other two options are going to be complete and average. So with complete, where we're taking the maximum value, and average, where we're taking the average of our Euclidean distances. So notice that these two almost look very similar, and a lot of times they are going to be. So with both complete and average, unlike with single where you end up with an unbalanced dendrogram, with complete and average you generally end up with a balanced dendrogram. So how do you tell the difference between the two? So in order to tell the difference, you want to look at your y-axis. So with complete, you're taking the largest value. With average, you're taking the average values. So if you form it on the exact same data, your complete y-axis will have a greater interval than your average y-axis. So here, the average y-axis tops off at about a little over 60. Complete goes all the way up to about 160, 170 for the exact same data. Because ultimately you're taking the greatest difference, here you're taking the average difference. So now I'm going to show how inversion can happen when we use centroid as our linkage function. So we're going to start off with 3 observations. So we're going to have 3 different groups. So group 1, we have 0, 0. In group 2, we have observation 1, 0. And in group 3, we have observation 0.5, 0.9. So in order to form our first group, we define our Euclidean distance between each of the possible groups. So from group 1 to group 2, from group 1 to group 3, or from group 2 to group 3. So our Euclidean distance from group 1 to group 2 is going to be 0 minus 1 squared plus 0 minus 0 squared. Take the square root, and we will get square root of 1, which is just equal to 1. From group 1 to group 3, 0 minus 0.5 squared plus 0 minus 0.9 squared. Take the square root, and we will get square root of 1.06. And then finally, from group 2 to group 3, we would just do 1 minus 0.5 squared plus 0 minus 0.9 squared. Take the square root, and we'll get a value of, again, square root of 1.06. So now we choose the smallest value, which is just 1. So our first grouping is between group 1 and group 2. So now we're going to have two groups, so group 1 and group 2. So in group 1, we're going to have 0, 0, and 1, 0. In group 2, we're going to have 0.5 and 0.9. So if we want to draw on our dendrogram, our first grouping, it's going to be at height 1, and it's going to be between observations 1 and 2. So now in order to form our second grouping, we're just going to find the difference between the Euclidean distance of our centroids, because we're using centroids as our similarity measure now. So our centroid in group 1 is just going to be the average values of our x1, which is 0.5, and the average values of our x2, which is 0. And the centroid for our group 2 is only one observation, so that's going to be the centroid. So we find the Euclidean distance now between these two centroids. So 0.5 minus 0.5 squared plus 0 minus 0.9 squared. Take the square root, and we will get a value of 0.9. So notice that the similarity between our centroids of group 1 and group 2 is less than our first split, which was at a height of 1. So if we were to draw this on our dendrogram, at 0.9, we're going to have our split, even though the grouping happened after the grouping of 1 and 2. So that's going to form this weird line where ultimately the grouping is going to be below the original grouping. So working our way up our tree, and then we go back down to form this grouping. And that's called an inversion. And it only happens when we use centroid as our linkage function. Now, thus far, we've been using Euclidean distance as our similarity measure, but you can also be using correlation. So with correlation, ultimately you're going to look at the trend of the way your variables relate instead of the distance between them. So for instance, if we were to plot this, say we have x1, x2, x3, and x4 on the x-axis, and then their values are just going to be on the y-axis. So here we have observation 1, which has an x1 value 1, x2 value 2, x3 value 1, x4 value of 4. So we can plot that like this. And then if we want to plot our observation 2, it'll follow the exact same trend. It's just going to be on a much higher interval. So we'll say 100 is right about here. Now if we were to use Euclidean distance, these two observations would be very far apart and very dissimilar, so it's very unlikely they would join until very high up on our dendrogram. But with correlation, these would ultimately be probably our first fused observations because they follow the exact same trend. So x2 is going to be higher than x1, and then x3 is going to be lower than x2, and then x4 is going to be much higher. And then if we were to do that with our first observation, it'll follow the exact same sequence. It's just on a smaller interval. So with correlation, you're not worried about the absolute values. You're only concerned with how they relate to, if we were to say plot them, and what trend they were following. So even if we added, say, another observation that looks something like this. So even though it's very close in Euclidean distance between our second observation, it would still fuse, or observations 1 and 2 would still fuse over this newly blue observation because the correlation that they share between their variables and the observations is much different. So correlation, you only look at the trends. You don't care about the absolute values. So now a quick wrap up. So this exam is focused purely on solving for the agglomerative method. So what agglomerative means is we're just going to start with all observations in their own group or individual groups, and then we're going to work our way up until we fuse all observations together. Now there's another possible method to create our dendrogram, which is known as the divisive approach. So with the divisive approach, we start with all observations grouped together, and then we split them apart one by one as we work our way down the dendrogram. So divisive, you start with them grouped together and you go until they're all in their own individual group. The agglomerative, you start with individual groups and then you fuse them together to the top. So now we can do a quick comparison between k-means clustering and hierarchical. So with hierarchical, before you run your algorithm, you have to choose your similarity measure and your linkage function. So with the similarity measure, we can choose Euclidean distance or some correlation. For linkage function, we can use single, complete, average, or centroid. Now with k-means clustering, all we have to decide on is our value of k. But a big disadvantage of our k-means clustering is that you have to choose the number of groups before you even run your algorithm. While with hierarchical, you create your dendrogram and then you can choose how many groups you want your data to be grouped into. Now, the results you get from your hierarchical clustering with different similarity measures or different linkage functions often create very different dendrograms. So oftentimes you want to run with either different similarity or linkage functions and then compare your results from those multiple dendrograms and then come to your final conclusion. But an advantage of hierarchical clustering is you don't have any local minimums. So no matter how many times you run your algorithm, you're going to get the exact same results. Where with k-means, we learned that you have local minimums. So you have to run your k-means algorithm multiple times, and you'll get slightly different solutions probably each time. So that wraps up this section. I hope you enjoyed, and I'll see you next time for principal component analysis. Thanks.